Okay. We're testing it. It thinks it's streaming. Just want to make sure I'm catching everything. I'm catching like the bottom of the screen. That's funny. Okay. This. It's getting there. I'm almost there, I promise. Fewer people today. I wonder if people dropped. Okay. It appears that it is working. All right, well, we're going to roll with this. Hopefully this will work. Let me just double check. Are we there? Hello?
Yeah, I'm moving. You're live.
I am live. You're seeing it. I wonder if we can hear it, though. Hopefully we can. Yeah, that's true.
24 August.
Yep. There we go. Okay. Well, we're going to go. We're going to make... Hey, I can hear me. I hate hearing me, but I can hear me. Okay, there we go. Welcome back, everybody. A couple things that I forgot to mention. First of all, thank you for coming back. Yeah, we have 5, 10, 13 people. We had like 14 before, so actually someone comes in a little bit later. So I think we're about the same size. So I'm not preaching to the choir. I'd like to make it worth your time to come to class. But you know you don't have to because it's all online. I just want to be real about it, right? We all have lives and whatnot. I'm not going to like penalize you for it. Although I don't know exactly when those quizzes are. They're not going to be this week, that's for sure. Other things. I forgot to mention that I prefer you call me Jonathan, not Doctor anything. I'm old enough as it is, and Doctor just makes me feel that much older, right? So I'd like to take that to make sure that, you know, we're all on the same page. I like to try to treat you as peers, and so not having that doctor in front of my name helps me that way. I know I have to still assess you, so there's still a little bit of a distance, but as much as I can. I mean, if we do our jobs well enough in academics, you should be our peer warden, right? Cool. So last time we got through a little bit of these slides with test theory and whatnot, and I'm going to go through these today. We'll probably do the EFA and PCA next week, because at the end of the week, we don't want to get me all angry about EFA, right? So I'm going to just do that, if you don't mind. Does anyone have any questions before we begin now? About anything we talked about before? Perfect. Then, here we go. We got up to talking about test theory. We did classical test theory, latent trait, the differences amongst the models themselves. So once again, I think we sort of left off here. There's these three major paradigms, if you want to call it that, three major measurement types of approaches that you'll see in the social sciences and education. Classical test theory, which I like to call the add stuff up model, right? Confirmatory factor analysis and item response theory. Right. And they're each of them, actually, we'll see the history of this, they all started sort of at the same place. Thank you, Jesse. Started at the same place in time, but they sort of went on different tracks. So you see little bit difference. There's sort of differences in terminology, but really the concepts remain the same. So if you learn one, it's good to know that how related it is to the other, because they start to the concepts, again, just all overlap so much. And one of those concepts, and what our first picture of that was what we call the score that comes out of the test, right? When you add stuff up, that's your true score. That's your estimate of the true score in classical test theory, right? In factor analysis, that's the factor score, and item response theory, that's theta. And you'll see theta, I don't know, theta seems weird to call it that. So you've got these families, if you want to call them that, paradigms of measurement models. Each of those is a type of model for data, right? So it's a mathematical representation of how people produce items, or better yet, how scores produce item responses. And in fact, I mean, classical test theory, we said the unit of the analysis was at the test level, whereas the unit of analysis is at the item level for the other paradigms. And really, when we get into the weeds of confirmatory factor analysis, you'll see that the assumptions that we make at the item level, we can make the same assumption across all the items, so we can yield classical test theory again. So it's sort of like this weird relationship. But the big difference between each of these types of paradigms, aside from test for classical test theory, item for everything else, is what type of item do you have? Does the item give you a continuous response? If so, it's confirmatory factor analysis. Does the item give you some type of categorical response, whether it's dichotomous? Sometimes we use the word polytomous. If you try to type that into Office or some other type of word processor, it will not like that. But that's also step 2. Polytomous response, that's an item response theory or item factor analysis. And we went through each of these types of terms.
Actually, I have questions about the item response theory. When you say it's categorical responses, I mean, you mean like yes, true, false?
Yes, but sorry.
True, false.
True, false is one type. It can be anything where you're coding it into some set of finite categories. So true, false, it would be one. Yes, no, correct, incorrect.
Yeah, actually, I read in the article like the reliability and measurement that there is a recent development in item response theory that is used in personality tests to, not mistaken.
Well, there's all sorts of new developments always in item response. There's an evolving research field, but the methods that you see aren't necessarily tied to one research area. So personality doesn't. Whatever's used there could be used elsewhere. But what did you see?
Actually, they said that it's been used to implemented because of the development of software. To this theory is used in like I believe, if not mistaken, self-esteem scale.
Yeah. Mm-hmm. Yeah, so that's one of the things. What you'll see in this, just as a microcosm of it, so somebody's studying self-esteem, and that's in personality theory. And they say, historically, what you see when people study latent traits or building measurement models is people start with classical test theory. And then eventually they move into something else. And usually that something else is factor analysis, confirmatory. But then someone comes along and says, wait, I learned IRT. Can I use it for these data? So you'll see that there. You'll see that in a lot of different fields. IRT, I did a paper with Lisa Hoffman, Mabel Rice, where we looked at the Peabody picture vocabulary test, which is a big, so it's a bunch of pictures. You ask people who are almost pre-verbal, but young kids, which one's a dog, right? Or whatever. We noticed that nobody had scaled it with IRT. So we put that together, mainly because there's a number of iterations. It's on like version 5 now. And the iterations weren't easy to compare. Mabel has a lab that's gone on for years over in the child language program, and she had version 3 data and version 4 data and version 5, and how do we link them together? Well, we built an item response model for it. So you'll see that every type of field that goes out there, what we sort of see this progression of where whatever they started with was classical test theory, and then the next measurement technique that gets built, eventually someone comes along and applies it. And whether that's applied in the 1980s or applied now, people are still evolving. So.
Just to be clear, because the confusion is that still using the IRT, they would use the binary system of scaling. Mm-hmm. So this is the confusing part, because if it's self-esteem, how they come to just 2 options?
Well, that's a design issue, right? How do you write questions for it? Usually a lot of those types of questions are I agree or I disagree. Like if you think of the MMPI, the Minnesota Multiphasic Personality Instrument, isn't that most questions are true, agree, disagree, true, false? Thank you. The counseling people come to rescue me. And that actually we're going to talk about at the end of this lecture. How you build the items really is important. And sometimes you pick true, false because it's unambiguous. But then again, what if you don't know, or what if you're somewhere in between? And so there's lots of ways of factoring that in. But yes, I don't know how they built it and why they built it that way, but that's certainly a design consideration that you would have if you were building a scale to try to test it. Other questions? Okay, yeah, see, I got to stand with a chair in front of me because I don't know why. I feel like teaching in this room, it seems like I shouldn't be standing, but then like sitting was weird the last time, so this is just... I'm awkward, I guess. Like, I should say like other academics, but no, I'm really awkward. Now this won't work, so that's even more awkward. All right, let's move forward. Or better yet, it is working. There it is. Okay, so the problems are in test theory. What we're doing is motivated by problems, particularly in education and psychology, right? So in education, and actually I shouldn't just leave it in psychology. It's social science is broadly construed. Who was in communication studies? So you've used these types of methods before as well. Political scientists have discovered IRT to scale judges or scale politicians. And not only that, in terms of legislation, how trying to come up with a continuum of conservative to liberal. So there's all sorts of fields, particularly in social sciences, that deal with this. What we do in education, often we use these types of methods to assess people's abilities usually, right? We want to give a person a test, get a score. Sometimes we call it a cognitive test, which is silly because every cognitive implies something going on in the brain, and then the opposite of cognitive is non-cognitive, which is something that now as education is like, hey, we should pay attention to, but that's still in the brain, so it's like, anyway, yes. You know what I'm saying? And it's all the same part of the brain, right? We're not talking like cerebellum, right? We're talking about like frontal cortex, right? Something like that. So anyway, getting into silliness. So we're in education, we build tests, particularly because we want to figure out what a student knows and provide a score historically. Not all the time, but that's the broad base of it. In psychology, oftentimes we're interested in the structure of the trait itself. Now, again, that's not always the case. In industrial organizational psychology, we build tests to provide scores to try to place people in jobs. And in education, sometimes before we, as we get more complicated versions of assessment, we need to know the trait better. We need to know the ability structure better. It's not just math. We want to know the structure of math and how different parts of knowledge interact to provide item responses. But by structure, what I mean is how many dimensions the trait have, what are the nature of those dimensions, how does that work with the items that you've built. So typically it's education psychology. Sometimes you'll see it in several independent groups, depending on which field you're in. But I would say, broadly construed, everybody who does this is social scientists or educational researchers. The cool thing about this, and also the thing that we're carrying around still, is that a lot of the theory was developed long before we had high-powered computers, right? And that, to me, is the legacy of why we have to deal with stuff like exploratory factor analysis. That stuff began back before we could compute things fast, right? So, and that was not good. So that's why we have a lot of the stuff that we see in exploratory factor analysis today. But since then, in the last, 50, 60, 70 years, since, your parents and probably grandparents have been alive, we haven't had to do the approximations that things have had to do. You'll see later on that mathematicians got involved, or statisticians got involved, and what had been thought of as a very, this community of test theory was thought as very, lacking in theory. That's the theory part. It was very fluffy. I don't know, is that a technical term? It didn't have like the solid mathematical rigor that you would see. Has actually come to do that in the last 40 years, right? We have a bunch of proof, a bunch of evidence, a lot of things that we can do to show that when things work, they really do work, and this actually happens well. So we're going to begin with my favorite topic, history. Let's hear that. But long story short, there was the Big Bang. And then eons went by, and in 1904, of our crazy system of figuring out how many years this planet has gone around the sun, Charles Spearman published 2 seminal papers. Have you heard of Spearman before? Where have you heard of Spearman before? Spearman and Brown, that's good. Did you hear about the Spearman correlation? It's like a non-parametric correlation that ranks. Yeah, he's a busy dude, huh? 1904, he published 2 seminal papers, which I don't know why you put that label there, but seminal. And one was talking about how to calculate the amount of error there was present in test scores. And that gave rise to classical test theory. That's actually where kind of the beginning foundation of it. How do we quantify error of a score, right? Which really talks about reliability. And so you see Spearman and Brown with the reliability coefficient. The other showed how to recognize from test data that whether or not the test measures just one trait, okay? Which is also big. Back for him, he thought there was one general intelligence out there, and that led to the development of confirmatory factor analysis. Hooray. Yay. So he sort of started off these two disciplines that sort of started barreling in different directions, although confirmatory factor analysis is much later than everything else. But classical test theory, again, the unit of analysis is the test, right? So here you've got a total score, and the typical formula that we provide for this is that the total score is equal to someone's true score. If we could observe what their true value happens to be without error, that would be, that would be nice, plus some whatever error that shows up at the time. The mean of error is thought to be 0. Error is thought to be uncorrelated with the true score. So, the theory, if, in the long run, if you could give a person a test multiple times and wipe their mind clean, their average of their score should be their true score. Ta-da. Right? The goal of this is to quantify reliability, because reliability helps tell you how much error there is in that score, right? A reliability of 0 means that when you get a score, there's absolutely 0 variance of error, right? And that score that you get on the test is your true score, right? Whereas reliability of something less than that means that score is sort of your best guess as to where your actual score is, but there's a range of values it can be. So there you go. Because this model did not include individual items, each of the items are thought to be interchangeable. Exchangeable is what the word statistic, right? Yeah.
Equal.
Yes, essentially equal. Right? There are certain statistics that we come up with that are not related to reliability directly, that we say some items are better than others, like blanking on it now. The point by zero correlation, item total correlation, for instance, or some version of discrimination. But they're not direct, you don't see that. So it's like, I don't know which item is best, I don't know which item is better. So it's just, basically, if you want to improve a test, add more items. Which items? Doesn't matter. As long as they're correlated, it improves the test. Right? Sounds scary, right? Because pretty much, as you know, with cognitive and non-cognitive testing, if you're getting the same results from inside the person's head, they're probably going to be related, because there's that thing called the brain. Right? So the unit of the analysis is the whole test. We want to figure out how much error there is in the test score. And error is something called a unitary construct. It just happens to be with the test, and so forth. So a little bit of history with it. Spearman came up with quantifying error from alternate forms or test-retest. Love that one, don't you? Then 1945, Gutman figured out how to figure out reliability from internal consistency, the correlations of the items themselves, which led to Cronbach's alpha, 1951. I think it's 52 before. And my mentor, Rod McDonald, would call that the Gutman-Cronbach alpha, so I insist on calling it that, but no one else does. They call it alpha or Cronbach's alpha. What you're going to see is that reliability is, like what you've learned of it, you need to unlearn a little bit, right? Each test has reliability. When we get into different types of measurement models, there is no one reliability for every test, right? Each score may have a different reliability. And that reliability may not actually be alpha. It's just what we call a reliability. It still stems from the same construct, which is the proportion of variance that's due to true score. But we don't call that alpha anymore. And in fact, if we just say reliability, that's neutral enough that everybody says, okay, that's fine, they'll pass. But if you call it some other name, like omega, which actually Rod tried to publish, or some other type of name, people are like, I don't know what that is. Like I was a co-author on a paper that came back where I put Gutman-Cronbach. I don't know what the Gutman-Cronbach is. Reliability. So yes. So you're going to have to unlearn that each test has a reliability. And what you're going to have to learn is each score will end up having reliability if we do things more precisely. And that reliability might change based on which score you have. Nobody wants to tell you that. Your GRE scores have differential reliability. Did you know that? In fact, two of you could have the same score, and one of your tests might be more reliable than the other. Nobody tells you that. Does that make you mad? Makes me mad. You each paid the same amount of money, but one of you got more accuracy in your result. Ugh. All right. Okay, so we go into confirmatory factor analysis. Confirmatory factor analysis is to build what we call a measurement model. That y equals t plus e is actually a model, but it's so plain, people sometimes don't even call it a model for a test. But that's our first measurement model there. It is a measurement model. What exactly a measurement model is? It's basically it's a mathematical statement where on the left-hand side you've got something involving the test. So in this case, it's the total. And on the right-hand side, you've got something involving the person's trait that you're trying to measure. All right, so there's the test score, true score, excuse me. In confirmatory factor analysis, we have a very similar feature. Left-hand side is test, right, or item though. So each item has an equation, and then those equations are regression models. Basically, we say the following: if we could observe your score, the true score or the factor score, or the actual value of the latent trait that we can't observe, but let's pretend we could observe it. What the measurement model does is says, if I knew this person's score was 3, I'm going to put it into a regression equation where there's an intercept and a slope, and I'm going to predict what the response will be for a person. Right? So if you have a test with 10 items, there'll be 10 regression equations. That's effectively confirmatory factor analysis. A bunch of regression equations. Right? Problem is we don't know the score, so we have to sort of work around that. Sort of like, you're going to do a study in regression, and you collected Y, but you forgot to collect X. Now what do you do? Don't worry about it. It sounds weird. We have ways to actually fix that, or at least the best we can. But we will figure that out. This differs from exploratory factor analysis that we'll see next week. That it's not really a model. Exploratory factor analysis is not really a model because it is actually overdetermined. Yeah, it's overdetermined. There's too many equations, too many parameters, not enough. Remember in linear and in algebra, a system of equations, you had to have the same number of unknowns that you had equations or constants, right? In exploratory factor analysis, there's way too many parameters than you have equations for. So you can't solve it. You have to make some type of constraint. And that becomes the issue. The issue then becomes what constraint. There's my summary for why exploratory factor analysis is bad mathematically. Well, how do you resolve that? Like in algebra, how did you resolve that? Exactly. That's it. That's the response for EFA though. I don't know. In CFA, it's different because effectively, and it boils down to that algebraic construct. Because we specify the number of factors we have, so long as we're specifying under the number of knowns versus unknowns, or so long as we specify a number of factors that fits that system of equations, we'll know what those are. We'll know what the values happen to be, and we'll be able to get a result that doesn't have to be up to, right? It's undeniable that this is the result. There is one result. It's identified as what we would call. So what we use... So what we do in CFA is we impose the number of the factors that are in a test, and we impose which items measure which factors. And not all items measure all factors, but we know that a priori. How do we know that? We wrote the test. We built the theory, right? That's sort of the other premise of why EFA is bad. How did you? Yeah. Anyway, we'll stop. I'll do that next week. So how do we do this? What do we use this for? We use it for, we want to analyze relationships among subscales. So if we have different factors, and we want this to be, the data have to be normally distributed or continuous to make this work well. The question that may be in your mind, which is, I've got a 5-point Likert scale item. Is that normal enough? There is no real good answer for that, unfortunately. So you're going to find that that's sort of in practice, it seems to be, at least in the social sciences and a little bit in education, if you have a scale and you've got 5-point Likert scale, that's okay to do CFA on. But if you've got the true-false thing, forget that. 2 points, no. Two options, no. 3 options, probably not. 4, maybe. And 5, it seems so. It's completely arbitrary. So what the purpose of why we teach multiple models in this class is because CFA is great for understanding what's happening at the item level, because it looks like regression and it works like regression. It's very direct. But then we'll quickly find out that not all our data are continuous. In fact, most aren't. So we'll want the proper way of really analyzing those would be like an item response model. But those are a little bit more complicated. But once you have the concepts down from CFA, because a lot of it's interrelated, we can switch, right? And so now you're not just learning IRT in this narrow window, you're learning it more in the context of, well, I have data that aren't truly normal or continuous, so I'm going to use this instead. So that's why this is there. It's more realistic that you have data that don't quite fit these assumptions either. I taught this class a couple years ago, and I was focusing on R. I hadn't taught in R before, and I didn't actually put in IRT. Right? I did it a little bit differently, and I got to the end of it being like, oh yeah, all I taught you before, probably not going to work too. You need to go take IRT. Nobody was really happy with that, so I'm trying to give you a little bit of each to know where to go. How we doing? Okay. I like this stuff. Can you tell me to get excited? I get loud or whatever. So what does this do? Here's your regression model right over here, right? If you had an item Y, for Y, the subscripts I like to use are the first letter of what it relates to. So I represents item here.
That's cool.
And S would be subject. And I wrote a book, I was co-author of a book on a different type of method. And we were trying to write it to broadly to fit in education and social sciences, and we ended up struggling that items seemed to be okay, but subjects, you didn't want to call people subjects, and APA says they're not subjects, they're participants, right? And in education, they're examinees, and you don't want to. And if you're in psychology and someone had an examinee, no, that's not true, and so it's like this. So you'll find I didn't realize that subject's a very charged word for some people, but I'm sorry, that's the one I typically settle on, unless I'm in diagnostic testing, which Jesse took last year, and then I said respondent because that was benign. It's like I had a focus group. How do you feel about subject? Ooh. How do you feel about respondent? Okay, we'll use that one. Anyway, this is a person's subject S's score to item I. Right? So if this was a Likert type item and they put strongly agree, maybe that was a 5. Right? And the regression would say, if we could observe X, which in this case is just a predictor variable, we would do what we typically do in regression, right? We'd predict the response to Y based on it. And there'd be some type of error associated with it. Well, in the confirmatory factor model, we changed the labels a little. We changed the notation a little bit, right? The intercept represents is mu, but that's still the same intercept. What do I mean? If that's the predicted value of the score when the predictor is equal to 0, right? So mu is the predicted value score when the predictor is the factor score. It's a thing we can't actually observe. That's the true score analog in factor analysis. So each person has a factor score, each subject. And if their factor score is 0, we think they're going to provide a response that gives us a value of mu. Right? Just like regression. Furthermore, the slope in confirmatory factor analysis is called the factor loading. Right? You've heard that term before, factor loading? A regression slope. Remember what regression slopes were in regression? How do you interpret them?
Change you expect for an increase in the input variable.
All right, for every 1 unit, factor score goes up. The expected response goes up by the factor loading, or the slope, right? Yeah, Jesse.
I haven't looked at it enough to process for the math, but I know in EFA the lambdas are somehow determined. I mean, they are eigenvalues in a sense, right? Or they're determined.
That's principal components.
So that's in PCA.
That's right.
So is there a linear algebra component? I'm sure there must be, but are these lambdas somehow related to eigenvalues, or is it just coincidence that we use the same symbol?
It's coincidence and historical that we use the same symbol. They are not directly related to eigenvalues, although they are related to values in the covariance matrix. Right? So if you have data, your correlation, for those of you, we're going to get to covariance in a little while too. The correlation matrix is, if you have a bunch of items, you can do some linear algebra on it, and there's these things that pop out called eigenvalues, which you don't need to know. Don't worry about them. But that's where the relationship stops. Okay. What we'll see is that this, by imposing this, and Jesse's in my program and he's been around for a few years. So have you guys remember the Godfather? Anyone ever watch The Godfather? It's a bloody movie. But there's this part of it where there's this police officer and like one of the main characters, and they're in a restaurant and they both speak Italian. And they say, I'm going to speak Italian with my friend, and they speak Italian to each other while this other person doesn't. So I'm going to speak Italian with Jesse here. If you're not into this, when you do this model, it prescribes a certain form to that covariance matrix, and then from that you can estimate the most likely values, just like you'd estimate the most likely values in a covariance. Now, if none of that made sense to you, I'll be teaching you Italian in the next few weeks, and you'll be able to hear that. Is that?
Yeah.
I maybe forgot in CFA could one item load on two factors?
Yes. Yes, you can have an item load on as many factors as you want, and that would look like multiple regression. I would say you can have on as many as you want, subject to, there's a couple constraints that you have to think of, and we'll get to those when we get to see it.
If our goal is simple structure,
If you want a goal of superstructure, but not always you do. And in fact, what we're going to see is that simple structure, we're taught in all of your measurement classes that a good item is an item that measures one thing. But that's not always the case, particularly when you have something like, let's imagine I mentioned to you before, the idea of the method factor. Like if you have to control for some other factor going on this, it's no longer simple structure. Right? If, for instance, if this is a negatively worded item, you may want to create a negatively worded factor, and there'd be two factors on this. But yes, there's other ways that would be important too, to how it works. So, other questions? Yes?
Can you give one example when there is no factor loaded in that model, like what that stands for?
So if this was not here, okay, what that would say, like if the factor loading was equal to 0, it would tell you that the factor itself was not related to the item.
Mm-hmm.
So in the same case that in regression, if this slope was 0, it'd say that the predictor variable did not predict the response of the person. The same thing would happen here. Furthermore, if you have if you have like 2 or 3 factors, let's imagine this is a factor 1, but factor 2 and 3 aren't on the item. It's basically saying that those factors aren't influencing the response directly.
I mean, our items are bad. They're not measuring.
Not necessarily bad. But if you get a 0 here, yes, it could be the case that they're bad items. It could
They don't load on the factor that we
That's right. Typically, it's saying this item is not measuring the construct the way you think it is. Mm-hmm. Exactly.
Don't you add some unrelated questions to obscure the intent of the?
You could,
Yeah.
but those if they're unrelated, they wouldn't be measuring the factor.
Yeah, so that could be the case.
That's right. That's right. So a lot of times there are measurement models you could build for those, although they don't fit into this class very well. But a lot of times what happens, like if you're on, like Amazon has this thing called MTurk, Mechanical Turk, where you can get a lot of data pretty quick, and they'll have questions. There are people evidently who get paid fractions of a penny per question, right? And they're clicking through these pretty quick, but they'll have these essentially error check questions or random, Yahoo, I don't know what they're called. Anyway, to see if a certain person's paying attention check items, right? And it'll say, circle the third option, or click the third option, or 2 + 2 is, or something that would be completely random. And often what you'll see in survey research is that people who fail those attentional check items will just be omitted from the data altogether. That's a little bit strong, but the measurement model that you'd have to build for that would have to assume sort of an attentional focus, and it gets into real complicated stuff real quick. But yeah, if you had a non-related item, it wouldn't have that factor that you're trying to measure on it. Okay, so we have intercept, which is still called the intercept, by the way. We have a slope, which is the factor loading. And we have this error term, which talks about, for each prediction, how far a person's predicted value is from their actual response. And in regression analysis, what we typically do with that prediction is we quantify the error variance. Right? We had, you don't go, when you take a basic regression class, you don't usually talk a whole lot about error variance so much, but it factors into how accurate your prediction is, right? If you had 0 error variance, right? That would mean everybody's E is 0. That means all the predictions are perfect, right? Or if you had very large error variance relative to the predictions, your R squared would be like 0, right? But you use it to calculate R squared effectively, right? And the same thing happens here. In CFA, error variance essentially is what we were calling error in classical test theory. It's our quantification of measurement error. It's what's left over after your factor predicts the item response. We actually call this, the term for it in CFA is called unique variance. Yes, yes, it's called the unique variance. And again, I'm probably going way too deep into CFA right now. We're going to spend like 2 weeks, and probably the way I talk, probably 2.5 weeks on it at least. So we're going to get into this a lot more.
Excuse me.
Yes.
In publication, like when they produce the semi-partial correlation, and they say this is the unique variance that measures X contrast.
Mm-hmm.
In this case, this is not accurate.
Right. It depends on the method they're using. It's usually when they say that, it comes from exploratory factor analysis, which is garbage. So. Yeah. So, sorry. Yes. I used to serve as a editorial board member for a journal called School Psychology Quarterly. Is anyone in School Psych here? It just used to be, right? School Psychology Quarterly is an APA journal, I believe, for School Psych. It's a fairly, I don't know if it's a good journal or not, but that was my first gig as like trying to move up the ladder academically. And I was convinced that was where whatever editor would assign me papers, they wanted them to die. They would send them to me because they'd be like, what? Like, they knew my response, because invariably the paper would be a CFA plus an EFA, which I hate, and then, or it'd just be flat out EFA, and it would always be that. And so my response would be, I wouldn't kill it. I would say, you have to redo all the analyses, and here's how. But yes, effectively they would say, well, it's negative, and so yeah, that's why. Okay, so if you think of this is the regression line. This is one factor with one item. If you have 10 items on the test, you'll have 10 different regressions, all at once. And if they're all measuring the same construct, let's say this is happiness, or this is whatever we call satisfaction, or subjective well-being, sense of well-being, satisfaction with life, I don't know, something like that. Let's go with something happy. That would be one factor. What we're going to assume is that each of the items are independent once we predict them with the factor. We call this local independence or conditional independence. Now in CFA, you don't have to assume that. In fact, you'll see some people who are not cool with the measurement part saying, well, yeah, item 1 and item 2 are correlated, even though I didn't explain all that correlation with the factor. And that's not cool, because the assumption of local independence allows you to say, literally, the factor is the only thing that explains the correlation between the items, right? So that's a big deal. We'll come back to that more later, and why people do that in the first place. So it's a linear model, right? So 1 unit change in F brings about a 1 unit change in Y. And if you plotted this, if you could see a person's factor score and put it on the x-axis and put a y on the y-axis, it'd be a straight line, right? So that linear model is great, except it doesn't work well if you have categorical data where there's a 0 or a 1. So we're going to come back to that in just a moment. Where CFA started with Spearman G. See, Michael. Spearman's G started it all off, and then later on, so Spearman was a big one-factor general intelligence person, apart from doing all the other stat work he did. And then in the 1930s, a guy named L.L. Thurstow, never heard of him before. Big deal in my field. He came along and said, "Nuh-uh, there's more than one factor, specific intelligences," and so they developed methodology to try to look for more than one factor. And that really was the beginning of exploratory factor analysis, which was extended on with Gutman's work. And then what you'll see back in the 40s was, if you had a GRA, if you were in grad school back in the 40s, your GRA was typically to be the computer. That was it. There were people who would spend years on one factor analysis because the calculations it would take to do, right? I don't know if you've seen pictures back in the 1940s also. Now, this is a more nefarious thing, but have you seen pictures of, in the United States, we have this thing called the Manhattan Project, where, we were trying to build nuclear warheads. But the pictures of that, there were the calculations for it. There used to be like these huge hallways of gymnasiums, and there would be desks lined up with people trying to do individual calculations and so forth. I don't know if you've ever looked this up, but that was it for factor analysis too. You were the computer. So your GRA was not collecting data or doing whatever your GRA might be now. It was literally trying to figure out one analysis. So it was hard to do, and things didn't quite work well. But then Lawley came along and found out, this is even before computers, found some really good properties mathematically, and that expanded into what we do now with confirmatory factor analysis. Jorskog really took it further, and so forth. But that brings us to item response theory, because it was, as we were getting better mathematically, understanding the mathematical properties of what this meant, we realized that when we took this continuous model and applied it to data that weren't continuous, it wasn't quite working well. So it came along with item response theory, which built along, started in 1950. Lazarsfeld gets talked about each, but there was also a person by the name of Frederick Lord who had a dissertation in 1952 that really was amazing. And item response theory began with the idea of a binary item. It's kind of your lowest level of categories. There's two categories for a response: yes, no, true, false, correct, incorrect. And what it uses is effectively a logistic regression. Right? If CFA is this linear regression, IRT is logistic regression. How many of you have had much logistic regression? A little bit? Not a lot. Okay, so we're going to dive into that many weeks from now, so I don't want to get overwhelmed, but that's just the big picture, right? Just put a placeholder on it. But you'll see varying types of IRT models. Right around the time, between when Lord's dissertation came out and a big book by Lord and Novick came out in the late 60s, there was a person named Roche. Ever heard of Roche? Who's heard of a Roche model? Roche model. The Roche people they're a cult. They're the Dianetics of psychometrics. I'm serious. They have these very strict beliefs about how things should be, but that's one of the types of models that are hearing it. It's a very restricted subset of an IRT model. This is one thing that's nice. There are no dyed-in-the-wool Roshis here on our floor. So like Billy Skrepsky and I we do the IRT. We both believe the same thing. A Roche model is an IRT model with restrictive assumptions. That's all it is, right? And they're testable, so you can see whether or not it fits the data. To the Roche people, those assumptions mean measurement is pure and wonderful, and they can go to their compound and trying to think of what else the cult people do. My co-editor at JEM, Journal of Educational Measurement, is George Engelhardt, who is a dyed-in-the-wool Roche. There was Roche, he trained someone named Ben Wright, and he trained George Engelhardt. And it's like, yeah. But no, I mean, we get along pretty well. I like George a lot. He just tells me that what I do isn't measurement, and I tell him he's part of the cult. But anyway, here's what happens. If you have your factor score, which we're calling theta, or ability often, in IRT, then on the y-axis, you don't have a continuum anymore. What you have is the probability of a result being a 1. Let's imagine that we have a 1 or a 0 for an item. Right, so we can pick one of those, where we usually pick a 1 because we're optimists. Place here. And what we're seeing is the probability if someone says true goes up, but it's a nonlinear function with respect to ability. And that's the difference. In a CFA, this wouldn't be a probability because it'd be this continuum, and each of these lines would be straight. It wouldn't be parallel because the slope would be different based on each one's factor loading. And you'll see these aren't parallel as well. There's an analog to the factor loading. But that's what IRT tries to do. It says, oh, the data aren't continuous. I'll change the y-axis, and that'll just change the way that our shape of our lines go. So I won't get into specifics yet. But again, here you'll see 1952 was Lord's dissertation that sort of started this off. Lord went to work at ETS after that, and that gave rise to your GRE scores. Look out. Lord and Novick, their book is fantastic. This 1968 text is amazing still, and that's like 50 years ago. So it's a great work. And then I said between 52 and 68 came out that Colt. Stop it. So there's this unified view, though, of test theories. We're talking about this to try to bring it all together, which is that classical test theory can be viewed as a restricted version of your common factor model or a restricted version of the IRT model. Okay. This theory has been around for a long time, so it's nothing new, but I like to teach it this way because you don't see it taught. We have classes for factor analysis, we have classes for IRT, we have classes for other topics. Let's put them all together. It's not that big of a difference, and multiply what you know about each from it. So IRT models are essentially CFA models if you've got categorical responses. CFA models are for continuous data. Either of these, if you put the right restrictions on, lead to your classical test theory. So we have it. But then we can even get into other types of data with it as well that don't have names, like if we have count data or zero inflated or something called two-part, which I won't get into.
So, just to confirm, can we organize these theories in terms of two aspects, the precision and accuracy?
Not quite. The aspects are test theory is effectively what is the model and what are the data. Those are the two aspects of it. But we'll get in. It does quantify the precision and accuracy. Each one of them will, and that's the result of it. So each one tries to quantify the accuracy of the model or the score, but what we can categorize them as, and really in this class, the model's the same. You've got the continuous trait. You want to use it to predict some type of response. What type of response is it? Right? Is it continuous? It's CFA. Is it categorical? It's IRT. Is it at the test level, or another way of saying that, do you constrain all the items to be the same? Then it's classical testing. Yes,
So
great.
what would you do with something like count? Like I know we do like Poisson, but when it comes to this,
You would do the same. It would just be a Poisson distribution. Yeah, what we're going to see is that each of these types of models actually imply there's a distribution implied by it or assumed by it.
Yeah.
And so for count, it's actually a little bit more complicated than Poisson because there's actually a number of different count distributions, but it's the same. You pick a distribution, and then the factor predicts the data through the use of what's called a link function to tell you the expected number of observations for this count. So
would that be more like CFA, more like IRT,
it's a little bit of both.
Oh, so it's like a joyous little intersection.
It is, yeah, absolutely. It is. Like the name for these kind of go away after a while. Just the way you think about it, the way I think about it is right hand side, left hand side, right?
Yeah.
That equation. Right hand side's data, left hand side's trait, and really I call it theory. Right? That's where the theory comes in. The items on the right hand side. So the distribution of it, what we're trying to limit is this feature that you see a lot in statistics, which is, my software only has this assumption of normality, so I'm going to do something to my data to shove it into my software. We want to create the software to fit with the data in its native format because there's a lot better properties when we do that. Okay, what are the advantages of this framework? We can test dimensionality. We can test whether the model fits the data. We can build concrete guidelines for which items are important for which scale. So we increase the validity of the scale in theory because we come up with a more accurate version of measurement from it. We can provide comparability across people and items, or groups even. We can test whether groups are different. So yeah, all of this provides better evidence for validity is one part, and better measurement of the trait for another. You want to take an abstract view of it. What are the disadvantages? Sample size is needed. All right, we need hundreds to thousands. Now, that being said, I have hope that if we sprinkle in a little bit of Bayes, that we can even make that better too. But we're not there yet as a field. It's coming. We also use really a lot of complicated math to make this work. So if you send someone a reference, that reference can be pretty complicated sometimes. So it takes a long time to sort of translate to the field depending on the level of proficiency that's expected in the field. Right? Furthermore, estimation can be very, very difficult. But we can still do this. What else? There's also a couple misnomers about this. This is sort of my experience here on this campus. When I first started working here in that building across the way there, we had a fairly prominent SEM advocate around who was very big into SEM. And basically, SEM would do everything like from washing your car to like telling you your scores or whatever. Okay? Do everything. But the same thing is true about it, CHS, that we see about all the other measurement models out there, or statistical models. Good models can't fix bad design or bad data or anything where there's a design flaw, it still can't help you, right? Bad items, if you write a bad item, it's still a bad item, right? And no matter what people call it, SEM is not, there's nothing causal about it, right? Causality is one of the options of a lot of options out there, right? So it's sort of an odd premise that people use the C word, causality, a lot. Okay, so in summary, test theory, it's awesome, but hard. But we're going to try to make it less hard. And by the end of this class, you're going to be able to tell your advisor, hey, don't do it that way. Well, actually, you probably won't want to tell your advisor that. But you could try to look at it differently. But let's talk a little bit about problems in measurement before we get out today. And just a couple things that we want to get into, mainly the items. This is the last thing. I'm going to assume most of the class that we have amazing items, but you're going to see, and many times when you look at someone else's scale, particularly those scales that are in the literature, the items aren't really that great. Like they're sort of thrown together. And so let's talk a little bit about that. Let's imagine we have a math teacher who wanted to construct 20 pass or fail items for a math test. Actually, let me skip these. Here are some of the questions we can answer. I'll go through this pretty quickly. Math teacher wants to figure out what people know about algebra and geometry, gives a test, and the teacher wonders, are there 1 score or 2 scores? All right? Geometry and algebra or just math? How would you know? And if 1 score is sufficient, how accurate is that score? Or how accurate would 2 scores be? Is 20 items sufficient to provide enough determination of knowledge? So we can also talk about test floor, test ceiling, and so forth. So we've gone into that. Here's what about the psychologist looking at depression? They have 5 options ranging from rarely to almost, and these are pretty terrible items. I have lots of energy. That's negatively worded. Sometimes I feel sad, and so forth. I cry. But there are other questions that are very similar. How many traits does this measure? How accurate is the score? How reliable is it? Is it biased to work against certain people? Right. So these are some similar questions that are going to work whether you're cognitive, what we call cognitive testing, or other testing. There's a great book by Mark Wilson in 2005 called Constructing Measures. It talks about the purpose of measurement itself. And he comes up with something called a construct map, where he tries to order people, which is, this is a terrible screenshot, but over here this is sort of a person's score, and it tries to order items with it as well. This is sort of a way of providing a validity evidence to say someone with this amount of score would answer this amount of item in a certain way, or this type of item that's this way. I'm trying to essentially quantify behavior of people and then concurrently figure out how items fall on that continuum. I mentioned the political example before. This is a good example of it, right? In our American political system that is seemingly right now and it's in a very not efficient state. Back when there were better years, people would talk about sort of a political spectrum going from conservative to Republican, conservative to liberal, right? And there's probably more to mention. Let's imagine there's this one. It's conservatism, liberalism. Probably could come up with another one, right? Let's just keep it one. And what they would try to do is you'd look at the different types of bills that people would vote on, right? And people would, the bulk of people tend to vote with their party, but not all of them, right? And so what you'll see is they'll put people on this continuum as well, and they'll put a bill on this continuum, right? And that bill would sort of represent, you know, kind of the part where a person would sort of reach their tipping point, or they may vote either way. You know, if you have a bill that's out there about universal income for people, right? You probably expect a large number of the Republicans to vote no, or the people conservatives to vote no, and as you get into liberal, there may be a fair chunk of those that would vote no as well, but at some point you get into the person who would say yes to it, right? So that's what this idea is. It's a construct mapped, and ultimately it sort of combines the two features what we're trying to do. Measurement is trying to put a number to behavior. In our case, it's test items, putting a number to how someone creates scores on test items.
So it's afterward, like after collecting the data, he come up with this template.
That's right, to map. That's right. It's one way to describe kind of the nature of the scale, right? A person who is, I mentioned before, like if you talk about basic income, if our scale is, you know, conservative to liberal, I don't know what we want to call that. Depending on your political orientation, conservatism or liberalism, right? Right? One of the two. At some point, a person who is going to vote is going to have a toss-up, going to have a really tough decision about the question of a bill, would represent sort of that level of where that bill would be. Because right? Above that point, everybody would say yes, and below that point, everybody would say no. Right? So the same thing could happen. This is terrible text. Talking about the speech-language hearing example of what types of sounds a person can make based on their age range, based on girls and boys. But you can't really read it well, so I'm just going to pass.
So it's a kind of using probability if you are in this range.
Mm-hmm. That's right. And what the threshold for probability we typically say is a 50-50 chance, right, for items that are dichotomous.
And this is should be employed when we discuss like either an item response theory or in confirmatory factor analysis, because confirmatory factor analysis, what I understood is that
it doesn't have probability.
Yeah.
But instead of we swap out probability for kind of where the mean is, where the intercept is. All right? Because ultimately, if we standardize our factor, if we put a mean of 0 for the factor, a person at 0 now has an expected response of the intercept, and that's exactly using a normal distribution assumption, which our factors do have, is where 50-50 would be.
That's our worst model.
What's that?
That's our worst model because you don't have any indicators.
Well, yeah, I mean, what we're trying to do is order items by the intercept rather than by where the 50-50 point would be. Yeah. Keep going here. So, but I wanted to get into, here's one of the other things I talk about, sort of how we construct instruments to measure things. We essentially have this idea of a construct we come up with in theory, and the construct, if it exists, indicates or provides that causal link to items, although we're not actually doing causality here, because we're not manipulating a person's value of the measure. But this is the theoretical picture of it, right? So if you have a certain value of happiness, you're going to respond a certain way to these happiness items, right? And those items, though, are written to have a certain what we call response space, right? Are they written in true-false? Are they written in Likert scale. Right? Is there some type of slider bar on your web browser that you can move over? Unless you're on the iPad and then it's right? And then there's inference, where we take the measurement model and we determine whether or not it fits, right? It's sort of based on the construct, but if it doesn't fit, we go back and modify our construct. Or perhaps then we modify our items and so forth. So it's like this circle of life of measurement. Hakuna Matata. At least someone got it. I haven't watched that movie in a long time. Yeah, anyway, I wanted to get into a couple things. How do we design good items? Because items are key. None of this flies unless your items are good. And what's good? Good question. There's some clearly bad types of items, though, right? But basically, how do you build items? You got to do your homework first, right? What's been done before, and be critical. What do you think might be wrong with it? But then, once you build a set of items, right, that's built under your mindset of how the construct maps onto language and whatever else. Talk to people about it. Give people those items. And the idea of a focus group, or better yet, an interview. This is where qualitative research would really make a big difference. How do people interpret what you ask them? Because a lot of times that's where it happens. Particularly if you've got differences in language, right? Or differences in translation, or differences in meaning. Or in our country, I mean, differences in region, right? We have different, although it's less than, it's not as big as some parts of the world, but it certainly could happen. So, it's just a case in point. I was part of a project, an NSF-funded project, several years ago. We were building a math test to study some type of proportional reasoning, which is basically how people interpret fractions, right? And there are several facets, 4 or 5 facets of it, and we had some really bright math educators who were building this. So they set up and they defined a construct, and they set a bunch of items out. And then these items we were trying to interview, where we were trying to assess middle grades math teachers for how they looked at this. Because this is supposed to be a big concept and trying to get kids into algebra. And in the middle grades, the teachers who were either trained as high school or mathematicians, which would be high school teachers, or you have people trained as early childhood education, which wouldn't have a lot in math training. Anyway, trying to help with PD, professional development. So we brought in about 20 people and did interviews. Think aloud. We had them take this math survey, this math test, and think aloud about each item as they were writing it down. And my colleagues realized the construct that they had built and some of the items they built wasn't valid. Wasn't what people were doing when they were answering the items. So they changed the construct, rewrote another test, interviewed another set of 20 teachers, felt comfortable about it, and then sent the test out to a national sample, right? Stratified random sample of teachers in the United States. And even then we threw out some items, right? So to do this well, it's an iterative process. Most of us don't have time for the iterative process, and we understand that. So, I don't try to pick on people in research because, you know how it goes. Your dissertation, you don't have the resources to interview 20 people and the time to do that. I get it. Right, but just think of this. You can talk to your friends. You can bounce it off of one person or something like that. That process is really important. But here's some tips for good items. Items are realizations of existing constructs. Right? How do I measure this construct? What's the first thing that comes to mind? Let's see here. Items should be unambiguous, of course. Right? It should cover a single concept if possible, without the word "and" in the middle. I think the word we used to use is double-barreled item, which I don't know what double barrel. What is that reference to?
Shotgun.
Oh, there we go. That's right. Double-barreled item. I've seen some triple-barreled items before. I haven't seen a triple-barrel shotgun though.
Hopefully we never do.
That's for sure. Items should be simple to process. Right? Negatives are harder to process. Double negatives are really hard to process. And try not to, one of the things I find most often, most of these people understand, but one of the things I find most often is kind of a common stem. Right? I feel like, right? Where if half of your items have "I feel like" as in the beginning part, and the other half don't, you might introduce this sort of idea of, well, people might respond differently or interpret those differently, right? So you want to make sure that the stem is not always there. You should span the full range of the construct, but not be too narrow, right? You can't write, there's only so many ways you can ask the same thing, right? For happiness, it's kind of hard. Are you happy now? You think you'll be happy tomorrow? Were you happy yesterday? Right? Have you been sad recently? I'm trying to think, like, what is, like, there's only so many ways that you can come up with good items unless you have a really, really detailed construct. So, and some not so good items. Here's some actual ones. Lisa actually found these. How important to you is it that my family members have good relationships with extended family members, grandparents, in-laws, etc.? What if you don't have grandparents, in-laws, etc.? My family is physically healthy. What if you don't have a big family? What if it's, like, I guess, or assess the quality of relationship that you have with your children. Okay, now I have children, but not everybody does, right? But this was on a survey that was given to people who may or may not have children. Where would you put that if you don't have, where would you write that if you don't have children? I don't know. To what extent did others make it difficult for you to engage in various activities before your imprisonment? This was given to a survey of people who were in prison and a control group of people who had not been to prison. Now, if you think about this, right, each of these items makes you go, probably should think about that a little bit more. But if you think about the way that you analyze the item in a classical test theory sense, we just add the scores together. They're going to be related, be fine, it's okay, right? Not right. Here's another one. It's hard to read, but there are...
The tutors.
What's that?
The difficulties in emotion regulation.
Yep.
Breaths and
Oh, is that it?
Yeah.
You know what this is even. That's awesome. Take a look at this. Look at this compounding valence, or the stem with the construct. Each of these are a different dimension. Some dimensions have when I'm upset leading off every item. Right? Some don't. So in that regard, how much is when I'm upset influencing each of these, right? It's hard to separate that. It can be very difficult to do. Or lack of emotional awareness actually has only reverse coded items, right? So here, in my experience, or when I'm upset. Anyway, so this is what happens with the items and how they can be different. It's really hard. There's only so much statistics can do to help. And the more you have to control for other factors on these items, like the method effects that we talked about, the harder it is to be precise in measurement of the thing you're really after, which is the construct. So just things to think about. It's really easy to say, that's bad, but how do you make a good one? It's a lot harder than it is, to say that it's bad. The other part is, how do you pick a response space, right? How do you pick it? Like, the most flexible is an open-ended response, or text, video, whatever, right? No interaction whatsoever. But it's really hard to code those. Really hard to get that into a format where we can try to take behavior or take thought and apply it and map it onto some type of measurement continuum. The least flexible are these multiple choice type. Which one of these options best represents you, right? So it's there are also other types of features of items that lend themselves better to the measurement models. So these open-ended, these multiple choice ones work really well. Or if you have a rubric scored version of an open-ended response, right? You can come up with one, although not always you can. The ones that don't work well are order from best to least, these options, right? What's your favorite ice cream? Flavor of ice cream, right? Vanilla, strawberry, chocolate. Like, which one do you like best? Well, if you have to put 1, 2, or 3 down, the measurement model for that has a really hard time because the items are those 1, 2, 3 choices are really dependent for each person, and the style of dependency is going to differ from time to time. So that's really difficult to put into a measurement model. Still can be done. It's just harder than others. So So yes, we're running out of time today. I just want to make sure. There we go. I'll just wrap up here. Any questions? Let me just this. So instruments are created to measure pre-existing latent constructs, pre-existing conditions, I guess. Those terrible in this climate of whatever is going on with the United States healthcare system. Latent traits with desired context. The whole building of items is really kind of not just science-based. It's sort of an art. You have to know a lot about the construct. You have to know a lot about the sample that you're going to survey. And you have to think about it, right? And plus, on top of that, you have to have a real good attention to detail about all of them. And what we're going to see in this class is we're going to assume this worked pretty well for the most part, that we have good items. The methods are pretty much going to assume that. But what happens if you have a bad item? Sometimes we can pick up on it. A lot of times we can, right? We're going to see that slope or that factor loading be 0 or close to 0. So it's not a lot of information about the trait of this item. But the better the items, the more information about the trait you'll get, the better the measurement on the trait will be. So that's that for today. I see 1:13 on my clock, 1:14. Questions? Okay, a couple little procedural things. At the end of next week, I have a homework 0 due. It's an extra credit. I have not yet put it up, but I will be putting it up on an online system soon, and you will get an email with information on it. It is going to take you 5 minutes and a copy of the syllabus to answer, right? And it's an open book homework. Mainly, it's to make sure that 2 things. Number 1, that you can get into the system and enter in responses. Number 2, that I can correct it if you can't, right? So it's sort of a trial run. And the second part of that, next week we'll talk about the first homework, which is due 3 weeks from Friday or 2 weeks from Friday. It's about a scale that you're familiar with and just doing some research on where it started. Kind of pull the original article, take a look at the methods they use to analyze it and so forth. But I will put that up as well. But again, no pressure. And I will actually go a step further. There will not be a quiz in here next week either. And any quiz that we do will be, again, conceptual. It will not be based on, slide 4 or whatever else. It'll be the big picture concept. So if you're following along with class and keeping up with everything, it should not be a problem. It should be a self-check for you, but also a help for me to figure out where I should need to spend more time. So, okay, thank you for your time. Have a great end of your week and a good weekend, too.
Yes.